All right, we're going to be looking at Group 1 FRQs today. So find that Group 1 FRQ packet. Also, if you didn't do so already, go ahead and go down to the description of this, and linked in there is a document that goes through all the terms that have very specific meanings on the AP test. All right, so now that you have your Group 1 FRQ packet, you've read through the terms in the document. I just want to kind of reiterate that every FRQ should take you about 15 minutes. There's 3 FRQs. We have 45 minutes to do them, so that's about 15 minutes per FRQ. All right, 2014 Mechanics 1. So what I'm going to do here is I'm going to identify some of those terms or some of those specific ones that I want to look at. So in Part A, it uses the word derive. That means I got to start with some sort of law. Now, most of those are right on your gold sheet. You want to start with those if you can. If it's not, you got to have like a definition or a law, something along those lines. Newton's second law, the definition of what velocity is. It's the derivative position with respect to time, something like that. If they ask you to draw a free body diagram, they're pretty good about reminding you, don't draw any components on there, only draw the forces. And if you're going to use the components later on, draw a separate free body diagram. They want to judge just the forces. They don't want any of their components on there. This one also asks you to justify your answer. Justifying your answer, this one's a tough one because you feel like you could write more about it, or you could just mathematically solve it. Mathematically solving it usually takes longer, but it's a definite way to justify your answer. Giving me just the relationships that the mathematics is going to show, that's usually the best scenario. Just walk me through the because therefore scenario in order to justify your answer. And Part C has the word determine in it. And so determines like derive, it's just a little bit more loosey-goosey. You don't need to start exactly with a law. But I tend to, when I see determine, I tend to even consider it a derive. Maybe I'll skip maybe the first step or something, but usually it's pretty much a derive. Some other ones that you're going to see, they're not listed on the sheet you looked at, but write a differential equation. So this one we did talk about earlier in the year. So if it tells me to write a differential equation for acceleration that can be solved for, that can be solved for velocity, really they want you to find something that says dv dt equals. In other words, solve for acceleration. But rather than saying write an equation for acceleration, they tell you to write a differential equation for velocity. Okay, so you got to be kind of sneaky about reading that one and knowing what they want. So you basically find acceleration and then substitute in dv dt. All right. Another word, whenever you see the words in terms of, this is very common when we have variables in there. We want to double check to make sure we are doing those variables. So what we're going to do next is we are going to actually go through this 2014 one. I'm going to walk you through the steps and kind of be pointing out what I did when I saw those terms. All right, so let's go ahead and set it up. All right, so we are going to look at this question, 2014 Mechanics number 2. So the first question asked me to derive in terms of the mass, the velocity when it reaches the bottom, and other fundamental constants known as g. So I looked at the problem and I saw a starting point and ending point. I'm thinking work kinetic energy theorem. They didn't give me the angle of the incline or the length of the incline, so they will all cancel out if I did forces in 1D motion, but because they gave me that height, I'm thinking work kinetic energy theorem. Now you and me, we're pretty familiar with work in plus work done by friction equals K2 minus K1 plus UG2 minus UG1 plus there's no springs. However, they might not be. So what we want to do is we want to start with something a little more familiar, more of a law. That's the derive portion of this. If this was determine, starting here is fine. Because it said derive, I'm going to look on my gold sheet, and I see on my gold sheet, I see work is equal to change in kinetic energy. And so I'm just going to write that first and then write this. They are going to be able to understand that I took this and I expanded it to that. Okay? All right. So next I'm going to cross out everything. So this is a frictionless ramp. There is no work in, no one's pushing on it. It starts at rest and it ends at a height of 0. And so I can then go ahead and say that, well, I'll move this over to the other side. So I have mgh equals 1/2 mv0 squared. Now, I made careful to write v0 here because in terms of v0. Now, if I had forgotten, whoops, I just went with my usual way of solving this and I started solving and I go, okay, m's cancel. That's nice. V equals the square root of 2gh. Oh, but they wanted me to solve for h, so then I changed that. So I get h is equal to v squared divided by 2g, and we're good. Now, this is where I want to double check because it's in terms of, so I see m, all right, there's no m, I don't have to worry about it. That always scares me, especially, I don't know, other people. If they tell me it should be in terms of something, I don't have it in there. But don't worry, sometimes they let people just have, oh, there's an m on top and an m on the bottom, you're okay. Oh, v0, but I put v. All right, I better check that and change that. So make sure it's in terms of the variables they want it in terms of, and I have g as well. So there's my answer. It's always nice to go ahead and box that in so that they know that that's your answer. All right, let's go ahead and take a look at part B. So part B is asking for the vertical component of the net force acting on the block upward, downward, 0. And this is when it's on that flat surface. Okay, so if it's on a flat surface going around in that kind of circle, the vertical component is 0. All right, so I'm going to say 0. And do they want me to justify that? Yes, they want me to justify it. And my justification is going to be there is no acceleration in the vertical direction. Vertical direction. So since there's no acceleration in the vertical direction, I can say that the sum of the forces equals 0. Okay, I feel like I've justified it enough. I've made a statement, and then that backs up the solution I came up with. All right, so the second part of this one then wants me to draw a free body diagram of the net force. So it only wants the single force. Now when I look at this picture and I see, all right, I have my block here, and it's going around, there are two forces I'm thinking about. There is going to be friction from the wall as it slides along that wall, and that wall is also trying to make it go in a circle, so there's going to be a normal force. So the net force is going to be a combination of those two. So when I draw my one single force on there, I will just draw a single force F net in this direction. Now you notice they put that grid mark on there just to show that, hey, I did see that it was going at an angle versus just purely out. Now my justification for this one is, well, there's a normal force and there's a force of friction, and the net force is the combination of those two. So it should be out and back, which would be in that direction. All right, let's go ahead and reset the board here, and we'll take a look at letter C. All right, so we have it set up to solve C and D. So C wants me to solve for the normal force from the wall. Now, I see my normal force from the wall. I notice my normal force is pointing radially inward because this thing is going in a circle. That normal force is causing circular motion, meaning I'm going to sum up the forces parallel to the radius and set it equal to MAC. Now they say they want it in terms of the speed it's moving at any moment. Oh, the speed it's moving at any moment is going to be inside that AC. So now I have just the normal force. Radially inward is my centripetal acceleration direction. I make it positive. So now I have normal force is equal to m times v squared over r. Now the radius, did they give me the radius of this object? Yes, but it was a capital R. So I want to make sure I make that connection so that I have it in the correct terms here. So now I have my normal force is equal to mv squared over r, and put it in a box here, as that is my solution. All right, what's D ask me to find? So D uses the word derive, where C used the word determine. So maybe in this determine, I can get away with this step. Derive, I might have to say, okay, I really know that AC is equal to V squared over R. This wouldn't hurt in this determine step to show a little more of your work, but it might not be as required as it is in the derive. Okay, so deriving the tangential acceleration means I'm now going to be looking at the forces in the tangent direction. Okay, so at first I was doing the forces in the radial direction here for part C. Now I'm going to be doing the forces in the tangential direction for this one. Now I'll note that the acceleration is in this direction. So I'm going to call that my positive direction. Also, you notice they use the word magnitude of the acceleration. They don't care about the direction because it's tangent. All right, so let's do that. So we are going to start with Newton's second law, so the sum of the forces, and I'm just going to use the word tangent here to the circle, I guess, is equal to ma, where a is my tangential acceleration. All right, so my forces, it looks like I only have the force of friction here. So I have the force of friction is equal to ma. All right, so the force of friction, make my substitution, it's kinetic because it's sliding, so mu sub k. So it's kinetic friction, so force of friction equals mu times n, mu k, I'm sorry, times n, where n is my normal force. Now they wanted me to use this capital N. All right, fine, we can use the capital N. I'm more comfortable with the lowercase n, but whatever. And then I equals ma. I'm going to bring my n value from here, mu sub k times m times v squared over r equals ma. My m's cancel, fabulous, and I get mu k times v squared over r. Just check, see what they used. Did they use a mu k or did they just use mu? They just used a mu, so I'm going to get rid of my k, just double checking to make sure my terms work out. And they wanted a magnitude, so if you would have put a negative sign along here, just take the negative sign off because all they want is the magnitude. Okay, so there we go. Let's go ahead, reset the board for the last part, part E, another derive, and this one's a little more intense. All right, so we got our answer in part D here. So now we just have to do part E, and part E wants me to derive an expression for the velocity. The speed of the block is a function of time t after passing point P on the track. Now, sandwiched right in between D and E here would have been a great place for them to put in, write a differential equation for velocity with respect to time. And so I would have said, oh, you want dv dt equals mu v squared over r. We already had it. They just want me to write it as dv dt because they would be setting me up then for this part E, which is solve this equation for v. All right, so in order to do that, I'm going to have to split up my dv dt. So now I have dv divided by v squared, so I got to get my v on the side with the dv, and equals mu over r dt. So now I need to integrate. Now this one's a little different, so I'm going to integrate it, and I'm integrating it from the time it was at point P, which I'm going to call time 0, to some time t after passing point P. And it's going to have some speed at that time t, but what was its speed at point P? Well, its speed at point P was v naught. All right. So I do need to do this definite integral, but I need to remember, oh, I have an initial condition. So two ways we can do this. We can either say, all right, this is my v naught, or I can say that v of t, well, v of 0, I should say, is equal to v naught. And then when I get my constant of integration over here, just solve and plug in v naught in that constant integration. All right, so let's go ahead and solve this out. All right, so the first step is I need to integrate these two sides. So the right side's pretty nice and easy, so I got mu t over r. Okay, and minus mu times 0 over r. All right, we're good. All right, so now I need to integrate this other side. All right, so let's just step aside here and let's make sure we know how to do these integrals. I'd hate for us not to, that is. Negative, this is v to the negative 2 squared dt that you want to integrate. All right, so we need to bring it down 1. All right, so I bring it down 1, so I get actually, I'm sorry, I bring it up 1. I don't even know how to integrate. All right, I bring it up 1, so I get v to the negative 1, and then I multiply, or I'm sorry, I divide by my new exponent. All right, and that's evaluated from v naught to v. Okay, so really I'm left with the negative 1 over v evaluated from v naught to v. All right, so let's go ahead and evaluate that and start solving for v. So here I'm going to put this in, and I have negative 1 over v minus a negative 1 over v naught equals mu t over r. And so the last step I need to do here is I just need to isolate this v. So we'll move this term over, move my 1 over v over, so now I have 1 over v naught minus mu t over r. So when I move this over, it became negative, so I minused it. When I move this negative 1 over v over, it became positive. And now I just need to inverse the whole thing, so I have 1 over v naught minus mu t over r equals v. And we have solved it. Now one thing you can do here at the end is just to check. So if I plug in 0, I should get v naught, right? Okay, so let's plug in 0. So this whole term goes away. 1 over v naught. Holy cow. All right, 1 over v naught, v. All right, and then what if I plug in something else, like infinity, for instance? Let's say I plug in t is infinity. If I plug in t is infinity, this bottom number gets monstrously large, and we end up with 0. Oops, I misspoke there. You can't do infinity because the force of friction, once it comes to a stop, the force of friction isn't going to accelerate it backwards. Once it comes to a stop, the thing is stopped. So what you could do here is you could solve for when is this equal to 0, and you could then essentially solve for the time it took to come to a stop. So sorry about that. All right, next we're going to look at the second part of this group 1, which is our 2006 Mechanics 3. So what I want you to do is go ahead and try this one on your own. Use the answer/scoring guide attached to the back of this. This is a great reference to see what are they looking for to give you points. And a lot of times you might find that, hey, I didn't know how to do this problem, but at least I wrote down that it was Newton's second law I was supposed to use, so I got 1 point. So think about that as you're like correcting your answer. What points could I have gotten that I would have known to write that. Okay, so look at that, use that, that's a valuable tool. At this point, yes, it's supposed to be taking us about 15 minutes to do these problems. Don't stress out if it takes you longer. Really work on working the problem. This is still our review time. We're trying to really learn this material. So don't make yourself think, oh, I got it done in 25 minutes. I never finished it. Don't worry. We will get that time down once we understand the material better. Okay?